What's up, scholars? We're going to be talking today about angular speed and velocity. We're also going to be talking about angular momentum and its conservation. Now, of course, to start our conversation with something angular or rotational, we should start with the linear version of that thing. So the first thing I want to talk about is the difference and similarities between linear speed and linear velocity. So linear straight line speed is defined as distance over time, but if we get really careful, which I'll admit we've not been super careful this year, and talk about linear velocity, its definition is displacement over time, where displacement is also a vector quantity. So if we talk about the difference between the two, maybe a simple example of how they might be different is a car driving down the road. So you might remember that when we've got something like speed, we just care about magnitude because it's a scalar quantity. So linear speed is a scalar quantity. We're just talking about the magnitude. So the speed of this car, I'm just going to make this up, let's say it's 50 kilometers per hour, and that's all we would need to describe the linear speed of the thing. Now, if we wanted to describe the velocity, remember that is a vector quantity, and vector quantities require both magnitude and direction. So if we wanted to accurately describe this, let's just say that this is going 50 kilometers per hour to the east. So notice for the vector quantity, we've got both magnitude and direction. The 50 kilometers per hour is the magnitude, the amount of velocity that we have, and east is the direction. So now we've got angular speed and angular velocity. Not surprisingly, angular speed, which we've talked a lot about, angular speed is represented by omega, by the way, is a scalar, just like linear speed is a scalar quantity. So to measure angular speed, we just did angular distance over time. Now, we've sort of got like four parts to this comparison. Angular velocity doesn't really exactly correspond to like an angular displacement, not exactly. Instead, there's kind of an unusual convention for angular velocity, and we would tend to write angular velocity with omega with a hat. So this is also going to be angular distance over time. And to find the direction of the vector, we need to use something called the right-hand rule. I'm going to write that down. So I've written that out. We use the right-hand rule, which I'm going to explain in a moment, to determine the direction of the vector for angular velocity. This will do that for other things. Technically, this whole time we should have been talking about how torque has a direction associated with it. Very soon we're going to talk about how angular momentum has a direction associated with its vector. So I want to try to explain that, and it's actually quite simple how to apply it. Alright, so let's imagine that we have got a spinning disc. We could say it's like a record on a record player, and we've sort of traditionally drawn the omega, the angular speed, in this manner. Remember, we calculated angular speed with the angular distance, that's 2 pi radians over the total time it takes to make one revolution, capital T. For angular velocity, which is what we've got here, gotta be careful. That's a vector quantity. That's going to be the same equation for angular speed, but it's also going to include the direction from something we're going to call the right-hand rule. So what is the right-hand rule? Let me try to show you what it looks like. I'm going to use my right hand. It's very important that that you use your right hand. In fact, if you use your left hand, you're going to get exactly the wrong answer. So we've got this thing rotating in a counterclockwise fashion. The right-hand rule just means you just take your fingers, all four of them, and you wrap them in the direction of the rotation, so counterclockwise in this case. Your thumb actually represents the vector for whatever you're talking about. In this very particular case, we're talking about
angular velocity. So what we would say is that the angular velocity points out of the page or out of the plane of this disk. So you have to forgive my very poor excuse for a hand, but here you can see it's curling in the counterclockwise direction, and wherever your thumb points, that's going to be the vector. So in this case, it's going to be pointing actually up like this of the angular velocity. So alternatively, if this was spinning in the opposite direction, we would curl our fingers, I'm going to try to show you this, in the opposite direction, and our thumb would point down into the page, or down with respect to these spinning disks. So that I don't confuse you, I'd like to actually get rid of this omega. If you're just writing in pen or pencil, you can just cross that out. We don't want to get confused with angular speed and angular velocity. In this case, it's a little bit weird, but we actually think of the angular velocity as being perpendicular to this surface in this case. It's at a right angle to the surface which is spinning, and then if I rotate it in the clockwise direction, it reverses. Again, we are using the right hand. We go in the clockwise direction, our thumb points downward or into the page. Just so that you can see this drawn a little bit more nicely, if we wanted to find out the angular velocity of this rotating wheel, very similar to what we just did, again, our right hand, you can see that very clearly this is the picture of a right hand. It will curl in the direction of rotation, and then wherever the thumb points, in this case, in this direction, then that is actually the direction of the vector for angular velocity. To just formalize that a little bit, here is the right hand rule for angular velocity. The fingers wrap in the direction of rotation, and then your thumb points in the direction of angular velocity vector. Very important, you must use the right hand. Why must we use the right hand? The answers are a little bit complicated. It has to do with calculus and some of the way these vectors will interact when we take something called the cross product. I'm sure most of you don't know what I'm talking about, and that's completely fine. To be very clear, you do not need to know the mathematics behind this. Why is it the right hand in particular? It's probably because most people are right-handed. I should mention this is, again, applicable to both torque and what we're about to talk about, angular momentum. So the next thing we're going to talk about is linear momentum and angular momentum. Like many cases so far in this topic, we are going to take the linear thing and basically just spin it. So if we want to recall, linear momentum is P equals mv, where momentum and velocity are both vectors. So if we have a mass that has some velocity, its momentum is just m times v. So for angular momentum, which symbol we use L for, it happens to be a vector, and we can find that direction through the right-hand rule. Let's think of what the analogies are between linear momentum's quantities and angular momentum. So the angular version of mass is the moment of inertia, and of course the angular version of linear velocity is angular velocity. So not much of a derivation there. We're just using this idea that we can go one-to-one from a linear quantity to an angular quantity. So what is regular old linear momentum? You can think of that as like the oomph that an object has. So for example, you could have something very small moving very quickly, like a bullet as an example, or you could have something very large with big mass moving slowly, like a big truck or an elephant, and that would have a lot of momentum. So what does it mean to have angular momentum? Well, that would be like I'll just draw like a sphere, for example. Something like a sphere with radius r, and we'll say it has some mass. This thing would have a moment of inertia of, I think it's 2/5 mr squared, and let's just give it some rotation speed, and it would then have, we can actually figure this out, an angular momentum vector that depends on its mass, its radius, and its angular velocity. So we can show what that would look like here. Just as an example of how we would apply angular momentum to a spinning solid sphere, we can insert some information. So the moment of inertia of this shape is 2/5 mr squared. So we'll plug that in for the moment of inertia I. And then, of course, the angular momentum, or sorry, the angular velocity we'll just leave as omega. And so this would give us the angular momentum. So again, this is just an example. The thing I want to figure out is the direction here. So this is rotating about a rotation axis. That's quite important that we figure out what is the rotation axis. Pretty clear here with something like a sphere. And we again apply the right-hand rule. So when we apply the right-hand rule to this sphere and it's rotating in the counterclockwise direction, the angular momentum vector would be up relative to the sphere. So the last thing we're going to address in this video is the angular momentum of a point particle. So you might notice earlier I gave you an example of something that has a pretty easily defined moment of inertia. We could just look it up in a table, and it's 2/5 mr squared. But what if I were to tell you that something moving in a straight line, like this ball, relative to some point of rotation, actually also has angular momentum? Even though this thing is moving in a straight line, it has angular momentum with respect to this point. For example, the planets in our solar system, moment by moment, are moving in a straight line as they go around the sun. They also have angular momentum. So we want to be able to figure out what that is for this. Now, we have to remind ourselves that the definition of moment of inertia for a particle is just mr squared. And we also need to remember that the definition of angular velocity is velocity divided by the radius, or the distance rather, from the point that we are talking about. So if we plug all of that in, we should get a formula for the angular momentum of an object. Notice that I'm just using the base equation that we developed a moment ago. So if I plug in the definition of moment of inertia for an object with mass a distance r from the center, it's just mr squared. And then instead of the angular velocity, I'm going to plug in its definition in terms of those other quantities, v over r, or the velocity divided by the radius. Now we can drop one of our r's from both sides, or rather from top and bottom, and we end up with the angular momentum being mv times r. So it's just regular momentum, mv, we'll keep our vector hat, times whatever distance you are away from the center. So we will look at that in some more detail. I should go back and clarify. This is the angular momentum of a rigid object. So I'll put that in parentheses. Whereas, oops, that should say object. And then this definition is for a point particle. It has a mass, a velocity, and is at a distance away from some rotation point. So that's all we've got in this video, folks. Thank you so much.